So we have a negatively charged particle shown below. This is the only particle that I'm looking at right now. First thing I need to do is draw an electric field lines around the particle, making sure to indicate the direction. When I have just one charged particle, electric field radiates outward in all directions, like the rays of a sun. The question is it pushing inwards or outwards? So which direction the electric field lines are going, you can find by using a test charge. Remember, a test charge is this hypothetical positive charge, which you imagine is there, and then imagine which way it would go if you looked at the charge. So if this positive charge were to see this negative charge, it would want to be attracted towards it. So the field lines should be going inwards towards the charge. Okay? And again, the positive test charge isn't really there, but in order to find the electric field lines and what direction they go, you imagine they're there. The actual problem is asking for, in part B, a point P, which is 15 centimeters to the left. So it's somewhere over here. Point P, 15 centimeters to the left. Again, you don't know what charge this is. It's a hypothetical imaginary charge, so we imagine that it's positive. But it is 15 centimeters to the left. Asking for the electric field, so I'm probably going to be using this. I only have one charge, so I can only use one Q. So to find that, I'm going to use KQ R squared K is the constant 9 times 10 to the 9th. Q is the charge that I have, which is this negative 9 microcoulombs, negative 9, 10 to the negative 6. Then divided by R squared, well, close, not 15, but 0.15. That's Alejandrina Aguirre. 9 e to the 9th. She's definitely blushing, by the way, as usual. We could take a picture of you and put it on there. E to the negative 6 divided by 0.15 squared. Whoa. So negative 3,600,000 newtons. I'm going to change to scientific mode. That'll help out. So negative 3.6 times 10 to the 6th. Oh, it's not newtons, it's electric field, so the units for this are newtons per coulomb, or you could even have volts per meter. As you can see later in the problem, it asks for volts per meter in electric field. So you can use either of those. So that's part B. As far as the direction, so that gives you the magnitude. This is the magnitude. The negative right there, that's not important. The direction is going to be towards, because this is just a positive test charge, so this is towards. Okay, part C, calculate the force and direction of an electron at point P. So this changes the problem somewhat. I'm still at point P. 15 centimeters, but now what I have is I have an electron, which is has a negative charge to it. And now I have two charges. I have the electron and I have Q, -9 microcoulombs. So to find the force between these two, I can either look at this original equation and just plug in both charges, or I could use this equation, which tells me that if I already know the electric field, I can just plug in the new charge and multiply. So QE. The new charge of an electron is down here, -1.6 times 10 to the -19th. And then the electric field I just found over here, I'm going to use the magnitude of it, so I don't care about the negative. And then just go ahead and calculate that. -1.6 E -19 times 3.6.
Isn't it -3.6?
E to the 6. And again, I don't need to have the negative because it's just the magnitude that's important. I can figure out what direction it is based on the charges in the picture. Multiply those together, you'll get this. -5.76 times 10 to the -13th. So again, this negative value only helps with whether it's going towards or away. So right now, if you ignore that, you should be able to tell if this electron is going to be going towards or away. If I have two negatives, this one's negative, this one's negative, this electron is going to want to go away. Okay, because like charges repel. So this may or may not even be negative. It probably shouldn't be, since this was negative. So that should be positive. But really it doesn't matter. It doesn't really change anything there. Last part, I'm looking for acceleration. Use trusty F equals ma. I know the force, which was just found here. 5.76 times 10 to the -13. The mass is of an electron, so if you look up in that table, the mass of an electron is something. Somebody help me out. Mass of electron. Anybody? 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 Electron, not a neutron. That was Leslie Rodriguez trying to lie to me. Leslie. Okay, clearer. What? 6 point what? 9.11 times 10 to the -31 times the acceleration. Then to finish it up, just divide by 9.11 times 10 to the -31, and that acceleration is I already have this. I'm just going to hit divide by 9.11 to the -31st, and this is my acceleration, 6.32 times 10 to the 17th. Acceleration is meters per second squared. Again, I'm ignoring the negative because all that tells me is the direction, which we already know is going to be accelerating away from the negative charge.